So in the last class we were discussing about optimality conditions related to optimization problems. For example, we took this optimization problem to minimize a function f of x subject to some inequality constants gix less than equal to 0 and I in some index set, suppose m from 1 to m, and also we have some set constants, and this is, we assume that this functions are convex. So we assume that this f and gi are convex functions, are convex, and the set omega, which is a subset of Rn, is also a convex set. Convex set. So under these conditions, this is actually a convex optimization problem, right? So we may consider the linear programming problem to be a special case of a convex optimization problem, because if fx is a linear function, so if fx is a linear function, which we have seen that we can write C transpose x, C1 x1 plus C2 x2, and we have this Cn xn. So this linear function is a special case of convex function because it is both convex and concave, and the inequality is associated with this because this feasible region, which we denote by this inequalities of a convex function. So we denote it by ax less than equal to b, and along with non-negativity constants. So this set omega, if we represent it like this, so this is also a convex set. So we can observe that a linear programming problem is also a special case of convex optimization problem, and the results we have seen, we may apply them to linear programming problems. So you may whenever you have a linear programming problem, you may try to use the conditions of this convex optimization problem to find out whether to solve this linear programming problem as well, right? So the theorem that we have seen for this condition, the Fridtjohn type necessary optimality condition, and we have seen this result that if this x bar in capital F, which was the feasible region, is an optimal solution of this objective function over the feasible region F, then there exists this multipliers. So we have seen that this lambda naught, lambda 1 and lambda m, and not all 0, right? Such that this condition that we were talking about, the Fridtjohn type necessary optimality condition, that 0 belongs to this lambda naught f of x bar plus we have this subdifferential of f of x bar, and then lambda I subdifferential of gi at x bar, I belongs to m, and then we have the normal cone to f at omega at x bar, right? And along with this, we have this complementarity conditions gi x bar is equal to 0 for every I in M. So, this was the Fridtjohn type necessary optimality condition, and why so here we are taking an optimal solution, and since we are dealing with convex optimization problems, and we know that for convex optimization problem every local minima is a global minima. So, therefore, we are taking an optimal solution, which means a global optimal solution, right. But if here in the case, if we do not have convex optimization problems, inequalities are not convex or the function is not convex, then we can treat it as a necessary condition for the non-convex optimization problem, and in that case the converse may not be true, and in place of an optimal solution we will talk about a local optimal solution. Okay. So, but right now we are dealing with this convex optimization problem, that is why we are talking about an optimal solution. So, now the problem with this condition is that this lambda naught, it is possible that this lambda naught is equal to 0. And if this lambda naught is equal to 0, then what happened? Then this term will become 0. And if this term becomes 0, then irrespective of the objective function, this 0 will belong to the feasible, this type of the feasible region only. That is, the effect of the objective function will vanish from this statement. So, that is why we need some extra conditions so that this lambda naught is not equal to 0, and these extra conditions are known as constraint qualifications. So, we have to impose certain conditions on the constraints of the feasible region so that this lambda naught may not be equal to 0. Okay. So, one of the constraint qualifications is known as Slater constraint qualification. Right. So, we can also write it like CQ, constant qualification. So, we say that the Slater constant qualification is satisfied for the problem P if and only if there exists some x in omega such that this gi of x is strictly less than 0 for every I in M, right. So, other than this x bar, if there exists certain x in the feasible region, so this is this set constraint. So, we have some point in this set constraint such that this gi of x is less than equal to 0, that is, it is not on the boundary. So, it is inside the boundary. So, if this conditions happens, then we will see in the next result that this lambda naught will not be equal to 0. So, this next theorem, which is known as the KKT condition which tells that assume that Slater's constant qualification is satisfied for the problem P, which is the convex optimization problem, then this x bar in F is an optimal solution of P, and now we have this if and only if there exists this Lagrange multipliers lambda 1, lambda 2 and lambda m greater than equal to 0, such that this 0 belongs to the subdifferential of f at x bar, and then we have this summation lambda I gi of x bar, I is in m, and the normal cone to omega at x bar, right, along with this complementarity condition is equal to 0 for every I in m, right. So the only thing that, so here it is if and only if, just because of the condition that we are dealing with convex optimization problem, right. So here, which is what is the difference between this result and the previous result, that here we are having this in place of lambda naught we are having 1, right. The other things are same, but only this lambda naught in place of lambda naught we are having 1. So here we can write 1, right, in place of lambda naught. So what we have to show now, that this lambda naught cannot be equal to 0, right. This lambda naught cannot be equal to 0 under the extra condition that we have imposed, which is known as Slater constant qualification. So we prove it by contradiction, right. So we assume that, so what we have to show, that we have to show that lambda naught is not equal to 0, right. So suppose, but then we suppose to the contrary that this lambda naught is equal to 0, right. So if this lambda naught is equal to 0, then what will happen? Then see, if this lambda naught is equal to 0 from this condition, right, from this condition, because all the other conditions are same except the one, Slater constant qualification. So what will happen? This 0 will belong to this set, right. So we can write that 0 belongs to this summation I in m, where lambda I gix bar plus normal cone to omega at x bar, right. 0 belongs to this. So it means that there will be some elements in the subdifferential of gi at x bar and some element in this normal cone, so that this combination will give you 0, right. That is, there exist some elements in gi, so we call it vi in partial subdifferential of gi at x bar I in m, and some element, say omega, in normal cone such that this combination will give you, this is equal to summation lambda I gi lambda I vi, I is in m, plus omega. Okay. Along with this, lambda is greater than equal to 0 and lambda I gi of x bar is equal to 0 for every I in m. Okay. This is from Fridtjohn condition, and we are assuming that this lambda naught is equal to 0. So now if we try to prove that, I mean this case is not possible, then we have to use this later constant qualification. Or in other words, under Slater constant qualification, this case cannot hold. So if there is some u in omega which satisfies Slater's condition, then, so what we can write, this 0 u minus x bar. So in the feasible region we are taking a certain u, suppose this is the feasible region, or I should make a convex feasible region, or like this, and then it cannot be on this boundary, so there will be some point u which will satisfy the Slater constant qualification. So we take that u, and this inner product with 0 is, of course it will be 0, but in place of this 0 now I can write this combination, because this summation lambda I vi plus omega u minus x bar, so it will be equal to 0, right? Yes. Which one? Yes. This is any u, okay, but this 0, we are, if you take inner product with 0, it will be 0, right? But this 0 is this one, because we are having vectors by Fridtjohn condition. So we are having elements in the subdifferential of gi and in the normal cone such that this combination is equal to 0. So in place of 0, I am just writing this number, or you can write it like this: 0 is equal to this, which is it clear now? Okay. So this 0 can be, so in this element is important u, because in place of 0 you can take any element that is immaterial, but now this element will play an important role because it is the point which satisfies the Slater constant qualification, right? So this can be written as 0 is summation. Now this we can, being an inner product, we can write it like lambda I inner product of vi u minus x bar and this omega u minus x bar, right? I is in m. Now what is vi? So we know that vi belongs to the subdifferential of gi at x bar. So we can apply the, since vi belongs to the subdifferential of gi at x bar, so what we can write? Vi belongs to subdifferential of Gi at x bar, that tells that this is Gi of x minus Gi of x bar is greater than equal to Vi x minus x bar, right? For every I in M. So, in place of this Vi x minus x bar, now x is any number, but now we are taking this u. So, this is u minus x bar. So, this value is less than, this value is actually less than or equal to Gi x minus Gi x bar, that is Gi u minus Gi x bar. So, this is true. So, this is less than or equal to Gi u minus Gi x bar, right? But what is lambda I? Lambda I is greater than equal to 0. So, if we multiply with lambda I, this product will also be less than equal to lambda I Gi u minus Gi x bar. So, we can write it less than equal to I in M lambda I Gi u minus Gi x bar, right? Okay, and we have this omega u minus x bar. Now, what is this Gi of x bar? I mean, if we talk about all the points which are active, if we talk about all the points which are active, if we multiply with lambda I into Gi x bar, this is going to be 0 due to the Fridtjohn condition. So, we will remain with this lambda I Gi u. So, this is actually equal to summation I in M lambda I Gi u plus omega u minus x bar, right? So, what is now, okay, so what is Gi u? This Gi u, because of the fact that we have assumed in the Fridtjohn condition that all the multipliers cannot be equal to 0, right? So, and we have assumed one multiplier lambda naught to be equal to 0. So, the remaining multipliers lambda I to all this, because Gi u is less than 0 for every I, and we have lambda i's which are greater than equal to 0. So, we have G1 u and maybe G m u and associated we have lambda 1, lambda m, but all of them cannot be, this is strictly positive and all of them cannot be equal to 0 simultaneously. So, there will be at least one lambda I which is strictly greater than 0, right. So, the product with that lambda I with Gi will be strictly greater than 0. So, this term is actually strictly greater than 0. Is it clear? Less than 0. Less than 0, right. Because we have assumed, we have obtained in the Fridtjohn condition that all the multipliers cannot be equal to 0 simultaneously, and we have assumed lambda naught to be 0. So, the remaining multipliers at least one will be strictly greater than 0, and corresponding to that multiplier the inequality constant, because it satisfies this later condition, the product will be strictly less than 0. So, when we add up, even if all the products are 0, at least one product will be strictly less than 0. So, that is less than 0. What about this? This can be less than equal to 0 by the definition of the normal cone, right. So, now this is less than, strictly less than 0, but is it possible? Okay. So if someone wants to prove that 0 is less than 0, this is the way to show that, right? But this is not possible. So we arrive at a contradiction thanks to this Slater's constant qualification. Okay, and that is why this lambda naught cannot be equal to 0. So when this lambda naught is not equal to 0, we can rearrange the multipliers. We can always rearrange the multipliers from the Fridtjohn condition or divide it by lambda naught. So which is a contradiction, right? Which is a contradiction. And due to this contradiction, we have this lambda naught is greater than 0 because it is greater than equal to 0, but it cannot be equal to 0. Now we can rearrange, right? So all the multipliers like lambda naught, so we can do this setting or whatever you want. I mean, it's already proved, but now we can take mu naught as lambda naught upon lambda naught, right? So the first multiplier will be 1 and all the remaining multipliers like lambda 1 or we can write mu 1 as lambda 1 upon lambda naught and so on, mu m lambda m upon lambda. So we can divide all the multipliers with lambda naught now in the Fridtjohn type condition, and we have the KKT type optimality condition, right? So this is one way we have proved that this holds when this is an optimal solution, that this will be the case, that we have this condition. Now the other way, because of the convexity of the function, right? So we assume, so what is the other way? We assume that there exist multipliers such that this condition is satisfied, and then we have to show that at that point, so for the other way we don't have to assume Slater condition, right? We don't have to assume any constant qualification. We just have to assume that this condition is satisfied with certain multipliers, and then we will show that due to the convexity that point will be an optimal solution, right? So let us assume that there exist this multipliers lambda I greater than equal to 0, I is in M, such that here we are not assuming this lambda i's are not simultaneously equal to 0. Why? Because already it is hidden in the objective function, right? Objective function, the multiplier is 1 in KKT condition. So now even if all the constant values are 0, for example, for unconstant optimization problem, suppose you are optimizing x1 square plus x2 square, right? And somehow x1 square plus x2 square, and we all know that 0 is the optimal solution. So if this 0, if the feasible region contains 0, so you don't need the need the multipliers associated with the feasible region, right? If all of them, even all of them are equal to 0, that makes no difference. The problem arises when the feasible region does not contain the origin, and then only this problem becomes different from the unconstant optimization problem, right? So that is why we try to adopt this different type of condition. So now we assume that there exists V naught in f of x bar and then Vi in subdifferential of Gi at x bar, I in M, and some omega in the normal cone to omega at x bar, right, such that this condition is satisfied, that is 0 is equal to V naught plus summation lambda I Vi, I is in M, and omega, right. So, when this is the case, then again we can apply the convexity assumptions of the functions, associated functions. So, for the previous case, you do not require any convexity assumption, right. The previous part that we have proved, we do not require any convexity assumption, right. But the only thing is that we have to replace the optimal solution by a local optimal solution, because we do not know whether that optimal, if it is a optimal solution, that then it will be a local optimal solution always, but it may not be a global optimal solution. So, we replace it by a local optimal solution if the case is not convex, otherwise it is identical, right. Then we have this, again we can write 0 is equal to 0 x minus x bar, and in place of this 0 we can replace it by V naught plus summation lambda I Vi, I is in M, and omega and x minus x bar, right. And again we can rearrange these terms, V naught x minus x bar, and this is summation lambda I Vi x minus x bar, I is in M, and omega x minus x bar, right. Now it's time to use the convexity of the function. So again this Vi x minus x bar associated with the subdifferential of Gi, right. So this term will be what? This will be less than equal to Gix minus Gix bar. So we can, and same for this thing. So we can write this is less than equal to f of x minus f of x bar plus this summation lambda I Gix minus Gix bar I in M, and we have this omega. So omega x minus x bar. Again with the same, see this lambda I Gix bar is equal to 0, yeah, equal to 0 due to the assumption, and Gix will be less than equal to 0 because x belongs to the feasible region. So this lambda I Gix bar will be less than equal to 0. So overall this term is less than equal to 0. What about this? This is also less than equal to 0. So we are remaining with this term which is less than equal to f of x minus f of x bar, right. And you observe that what is this? This tells that f of x bar is less than or equal to f of x for every x in the feasible region f, right, which tells that x bar is an global optimal solution of the given optimization problem. So for a convex optimization problem, this is if and only if condition, that is a characterization of the global optimal solution, right. And if the optimization problem is not convex, then what we do, we can replace the global optimal solution by a local optimal solution, right. So in this case we have seen a very important property of constraint qualifications, which is very useful, very important, because due to that constraint qualification we can avoid that the multipliers associated with the objective function is not equal to 0, right. And not only a Slater constraint qualification, in literature you can see many other constraint qualifications like linear independence constraint qualification, Mangasarian-Fromovich constraint qualification, Abedi constraint qualification, so there is a lot of literature on constraint qualifications. So let us try to see another constraint qualification for this. Is it done? Okay. So for a special case of this problem, which we are going to take as a differentiable functions, right. So suppose these functions are differentiable, then what will happen? So in place of yeah, no, I am telling that if the function is differentiable now, then this subdifferential will reduce to the gradient of the function, right. Okay. So for the differentiable case, we are going to have this Fridtjohn type. So if all the functions are differentiable, okay, at x bar, and we assume that this omega is equal to Rn, then x bar in the sense of the previous result in the Fridtjohn type condition. So by the Fridtjohn necessary optimality condition, one has, so we are going to have this lambda naught gradient of f at x bar plus summation lambda I gradient of gi at x bar, I is in M, is equal to 0, right. And this can be rewritten as lambda naught gradient of f at x bar plus I is in M of x bar, right. Lambda I gradient of gi x bar is equal to 0. Why M of x bar? Because if it is not in M of x bar where the constants are active, this this will be less than 0, so lambda I will be equal to 0, right. So whenever we are not at I does not belongs to M of x bar, lambda I will be equal to 0. So we can exclude those things, right. Now what will be the assumption? We will see, suppose that again we are approaching from Fridtjohn type optimality condition and trying to find out a condition which will guarantee that this lambda naught will not be equal to 0. So suppose that this lambda naught is equal to 0, then we have, so if it is 0, then what will happen? This summation lambda I is in M of x bar gradient of gi x bar is equal to 0, right. Suppose we have an assumption that all these gradients are linearly independent, right. So, suppose these gradients are associated with these active constants are linearly independent. So, since this gradient Gi x bar, where I is in M of x bar, are linearly independent, right? Therefore, see, if this is equal to 0 and all these gradients are linearly independent, what will happen? The multipliers will be equal to 0. Therefore, this lambda I will be equal to 0 for every I is in M of x bar. But now it is a contradiction, right? Because we assume that lambda naught is equal to 0 and all the lambda i's are also equal to 0, okay? Which is a contradiction, and hence this lambda naught is not equal to 0. So, again we have this result, but when, so the result is that it is called as, the constant qualification is linear independence constant qualification, right? So, if gradient of Gi at x bar, I is in M of x bar, are linearly independent, then LICQ is satisfied at x bar, right? Linear independence constant qualification is satisfied at x bar. So, in the previous Slater constant qualification, that was satisfied for the problem P, not at any point, but here it may vary from point to point, okay. So, at a certain point, if the gradients are linearly independent, of course, for this differentiable problem, then we have this KKT condition, right. So, we have seen another constant qualification LICQ, linear independence constant qualification. So, from this Fridtjohn type necessary optimality condition, if we add a constant qualification, we get KKT type necessary optimality conditions, and so we can write that Fridtjohn conditions plus constant qualification will give us KKT conditions, right. And for different optimization problems, we may go for different types of constant qualifications which may be weaker than the linear independent, like which, so we try to find out conditions which are weaker than the previously known conditions. Like if we have linear independence constant qualification and we go for Mangasari and Fromovich constant qualification, then we will see that this MFCQ is weaker than the linear independence constant qualification. So, we try to find out weaker conditions under which this lambda naught should not be equal to 0, right. So, maybe we end now with this one exercise. If you want to do that, to minimize this objective function x1 minus 2x2 subject to x1 square plus x2 square less than equal to 1, right. So, you can use the k, and you see that this is linear. So, it is convex and this one is also convex. So, this is a convex optimization problem. So you try to find out the conditions or KKT conditions where this is satisfied, right? So you work out this example. Try करिए. So here f of x is equal to minus x1 minus 2 x2, and so we have only one constant, so we can write g1x is x1 square plus x2 square minus 1 less than equal to 0. Okay. And Professor Ligaj has explained many in consumer theory. He has used this KKT conditions for the differentiable case and try to find out how that KKT condition works. So this KKT condition is very important to find out the optimal solutions of this, of different types of optimization problems in different fields. We have to figure out what are the constants and objective functions, and then we can apply it, because this is a general condition, but as per the requirement of the problem we can use it, right? So now what will be the conditions? So gradient of f at x you can write minus 1 minus 2, and gradient of g1 at x we can write 2x1 and 2x2, right? So now we can, so we need only one multiplier, and maybe it will also be required in duality theory, this KKT conditions. So in duality theory they are also, to formulate the dual of the primal problem, this KKT conditions are also required. So now we are having this, what will be the condition? This 0 must be gradient of f at x bar plus lambda 1 gradient of g1 at x bar, right? But we don't know this x bar, we don't know this x bar. And then we can write this 0 is equal to, you have minus 1 minus 2 and lambda 1 g1 x bar 2 x1 and 2 x2, maybe x bar, and then along with this we have lambda 1 g1 at x bar is equal to 0, it must also be equal to 0, and this lambda 1 is greater than equal to 0. So these are the conditions that we have to observe to find out the values of x1 bar and x2 bar. So that will give you the first one, minus 1 plus lambda 1 2 x1 bar is equal to 0, and minus 2 plus lambda 1 2 x2 bar is equal to 0, right? And this lambda 1 is greater than equal to 0. And what is g1? g1 x bar is x1 square plus x2 square, x1 bar square plus x2 bar square minus 1 is equal to 0, right? Now what are the possibilities of lambda 1? Lambda 1 has two possibilities, right? If you increase this number, then the possibilities will increase, right? But now for the simplest case we have only two possibilities. If lambda 1 is equal to 0, then what will happen? If lambda 1 is equal to 0, then minus 1 is equal to 0 and minus 2 is equal to 0, which is not possible, right? Which is not possible. Then we have a contradiction, right? So this so Hence, this lambda 1 is greater than 0. Lambda 1 is greater than 0. And whenever this lambda 1 is greater than 0, we can write x1 bar in terms of lambda 1. Okay. Thus, we have x1 bar, we can write here. So, then this x1 bar can be written as 1 upon 2 lambda 1. 1 upon, sorry, is it? Yes, 1 upon 2 lambda 1. 2 lambda 1 and x2 bar is equal to 2 upon 2 lambda 1. Huh? 1 by lambda 1, right? So, we have values of x1 bar and x2 bar in terms of lambda 1, and then this can be applied here. Why? Because lambda 1 is greater than 0. See, all these conditions are to be used to find out a possible value of the point where these conditions are satisfied. But that point may not be an optimal solution, even if it satisfies the KKT condition for a non-convex optimization problem. For a convex optimization problem, it is equivalent. But yes, KKT point, but that will help us to screen out the feasible reason, like we do in linear programming problem. So, in linear programming problem, the instrumental condition is that every optimal solution, if there exists an optimal solution, then there exists a basic optimal solution, right? So, that basic feasible solutions are instrumental in linear programming problem, and these KKT conditions are equivalent to non-linear optimization problems, because it helps us to screen out the feasible reason to find out the optimal solutions, right. So, now we can use this also, lambda 1 is greater than 0. So, you can apply this result, x1 bar square plus x2 bar square minus 1 should be equal to 0, and then you can apply this. This is 1 upon 2 lambda 1 square plus 1 upon lambda 1 square equal to 0, right. So, what is the value of lambda 1? Root 5 by 2. So, lambda 1 is root 5 by 2. So, if it is root 5 by 2, you have the values of x1 bar and x2 bar. So, that gives you x1 bar as 1 upon root over 5 and x2 bar as 2 by root over 5, right. So, by using this KKT conditions, also of course, this is only one inequality constant. So, it is not very difficult, but it can explain that how we are using different conditions to find out the optimal solutions. And of course, you have seen many other applications of KKT conditions by lectures given by Professor Ligaj, right. Okay. So, maybe with this we can end this tutorial now, and hope that this was the last tutorial of the course. So, hope you have learned many things. Of course, we have remaining 2 lectures tomorrow, and hope you have, of course, you have learned many things from this course. Okay. And even if you haven't learned anything, you have the seed inside you now.